All right, so the goal of this video is to just go through some basics and logistics of sequences and of series. And just, again, to be clear, because it's easy to get the two terms mixed up. A sequence is just the list of the numbers. So 1, 2, 3, 4, 5. That's the sequence of the first 5 numbers. A series would be the sum of those numbers, 1 plus 2 plus 3 plus 4 plus 5, if I add them up to get to 15. And so a lot of times we don't intentionally mean to interchange them, but sometimes we do accidentally. And it's really important, especially this first couple sections, because some of the questions are going to ask just about the sequence of terms. Some of them might ask about the summation or the whole series of the terms. Okay, so sorry. Okay. So if I look at like this first example, like the a sub n here, a sub n equals n over n plus 2. I could list out like the 10th term if I wanted, or I could say, oh, I know what the 10th term is. The 10th term would be 10 over 12, right? Or if I wanted the 100th term, there's 100 over 102. The 10,000th term, 10,000 over 10,002. And so, I'm wondering, are these terms converging to a certain value? Like, are the terms themselves getting closer and closer to a particular number? And in this case, they are. They're getting closer and closer to 1. And how do and how do I know that? How do I analyze that? So that's sort of up here. So a sequence of terms is said to converge if you know its limit exists. So if I find the limit as n goes to infinity of a sub n, which is the limit as n goes to infinity of n over n plus 2, because I'm approaching infinity, I guess I could do one of two things. I could use L'Hopital's rule, since it's infinity over infinity, do the derivative at the top, which is 1, the derivative at the bottom, which is also 1, so I know its limit value is 1. Or I could realize that it's going to behave like their powers in terms of like the highest exponent. So it's like an n over an n, which is 1. So I know that the limit exists, and because the limit exists, I know that the sequence itself converges, and so I could say the sequence of terms converges. Sequence of terms converges, and I know it converges because the limit exists. And again, it's just the sequence, has nothing to do with adding them up. Now, the second one, this is a geometric sequence. So the first term is 5/3, and maybe I've wanted like the second term, that's 25/9, or the third term, that's 125/27. And so if I want to know, well, do the sequence of terms here, do they converge? So you could apply the limit as n goes to infinity of a sub n, which is 5/3 to the n, and because our terms are getting exponentially larger, in other words, this limit is equal to infinity, if you will, we would say that the sequence of terms diverges. Sequence of terms diverges because the terms don't get any closer to a particular value like they did in example A. So sequence of terms diverges. Okay. Now, again, a lot of this is here's a new word or here's a definition. Here are some examples. So an alternating sequence alternates positive, negative, positive, negative. So if you wanted to analyze an alternating sequence, we can say that the sequence of terms either converge or diverge, or we can analyze that, right? So an alternating sequence of terms converges if the limit of its absolute value equals 0. And so again, it's not talking about the summation. We're not talking about a series yet. We're just talking about the terms themselves. So you could have an alternating sequence like 1, and then maybe negative 1/2, and then positive 1/4, and then negative 1/8, and then positive 1/16. So there's a sequence that alternates, and we can show that those terms, if they approach 0, then the sequence of terms converges. Doesn't say anything about the sum. even though I know something about that sum. So how do we verify that? How do we analyze that? We have to analyze it as an absolute value. So we know this alternates because of that -1 to the n. Anytime you see that -1 to the n, it alternates. And again, if you're not comfortable with some of the notation, then certainly take some time and list things out, right? So go ahead and list out the first couple of terms when n is 1. So that's 1 over 1 squared minus 2. So that's a -1, but then that also makes that negative, right? So you'd have like a -1. And then, sorry, -1 over -1, which is +1. I apologize for that. There you go. And then, maybe list out what happens when n is 2. There you go. I thought I picked the pen. There it is. -1 to the second power, that's a positive number. And then 2 over 2 squared is 4. 4 minus 2 is 2. So 2 over 2, which is also 1. And then 3, so now we have a negative value. And now I believe, now it should be becoming its alternating piece, because now everything above that will be positive. 3 squared is 9. 9 minus 2 is 7. So here's a case where the first, and the next one will be 4. The first two terms don't quite fit the alternating sequence pattern, but that's okay. The rest do. And so, if you want to start analyzing that, but overall, if you take its limit as n goes to infinity of the absolute value of this. Now, when I write that as an absolute value, that means I can get rid of the -1 to the n. I can get rid of the alternating component. So that's just n over n squared minus 2, like that. And again, thinking about, well, these, like, n is going to infinity. These are natural numbers that we're counting, so n's already positive. So in theory, I don't even need the absolute value bars anymore once I've removed the alternating component. As n goes to infinity, the larger number is terms of an exponent, right? Because we're looking. Looking for the pen. There it is. So we're looking for which power takes over, and a quadratic, a square, is a higher power than the numerator's power. So we know that limit does in fact go to 0. So if it goes to 0, then we know that the alternating sequence of terms converges. So we could say the sequence converges, or sequence of terms. I like to use that because it just talks about the terms themselves, not necessarily the whole summation. Okay, so here's another alternating sequence. And so again, I want to analyze, do the terms converge or not? So I would do the limit as n goes to infinity. Now I could say of absolute value of a sub n, like that. That way I know, oh, okay, so I'm going to remove the alternating component. So I just have to focus on the limit as n goes to infinity of n squared minus 3 over n squared plus 5. Well, here they have equal powers, so that limit's equal to 1. So this alternating sequence does not converge because its limit of terms does not go to, does not go to 0. So then I would say that this sequence of terms diverges. If you remember last semester, I talked about sort of like death by oscillation, because you're oscillating back and forth between two values. That's sort of what's happening here. Because the terms themselves are getting closer to 1 in absolute value, that means as this alternates, one term will be close to +1, and then one term will be close to -1. One term will be close to +1, one term will be close to -1. So, so again, I kind of have that weird concept of death by oscillation. Okay, let's do two more vocabulary words that sometimes come up. This word bounded and this word monotonic. Okay, because if you are both bounded and monotonic, here's another way to show that your sequence of terms converges. And so I think a lot of us have a good understanding of bounded, but just to maybe have a little bit more of a rigorous or more formal definition, a sequence, we could say a sequence is bounded above. So there'll be a bounded above or a bounded below. So I could say a sequence, A sub n, So do that nice little bracket. So a sequence A sub n is bounded above if there is a real number, we'll call that real number m, capital M, such that every A sub n is less than or equal to m for all n. Right. So I mean, so you just know what the upper value is, and every other term is always going to either be less than it or equal to it. And we could sort of change the direction to say, what does it mean to be bounded below, right? So a sequence A sub n is bounded below if there's a real number, and maybe I'll call that number n, capital N, such that A sub n is always greater than or equal to n for all n. Now, I like using, more formal things because as you go on, upper level mathematics, you're going to notice that there is, especially, I know it's a comment I get from a lot of students who I had last year in BC, who are going into multivariable, into linear algebra, how formal things are with just definitions and symbols. And so it's just good to start thinking about that, even now. Okay. So what does it mean to be monotonic? So then to be monotonic, it just means that all your terms are either non-decreasing or non-increasing. So there you go. So all terms are either non-decreasing. I'll show you with example in just a second. So non-decreasing meaning A1 is less than or equal to A2 is less than or equal to A3, less than or equal to A4, less than or equal to A5. Okay, so they're not. So they might be the same, but they're always getting a little bit bigger, or worst case, they're always equal. So monotonic in that direction, or all terms are non-increasing. And then you could just flip the inequality that way. And A sub 4, A sub 5, etc. Okay. And these don't always, these don't come up like all the time, but every once in a while you'll see like one of these vocabulary words. So I sort of wanted to talk a little bit about that. Okay, and then I think, again, we'll do another video for some more notes, and I'm anticipating there's probably a series of 3, just because there's so much I want to talk about and give you some background, so we're all kind of starting on the same playing field.